What you've just heard are some of the noises that we'll be analyzing in this webinar. My name is Davide De Carvalho, and with my colleague Filippo Tosato are working on two linked projects called MilJet Sound, MilSound 2, under the supervision of Professor Benoit Marinos, Harry Christophe and Francis Moni. The objectives of this PhD is to improve the capabilities of the existing numerical solver in order to better noise propagation prediction, with the final goal to improve our capabilities to have informed decision on noise mitigation strategies. Within this webinar, we'll discuss the motivation behind our research, to then dwell on the physics behind noise propagation with a special attention of how humans perceive noise. We'll then discuss the difference between linear and nonlinear propagation, which is at the core of our PhD researches. And finally, we'll have a brief showcase of the model that we have so far been developing. The motivation behind our research is that noise, according to the World Health Organization, is the second biggest pollutant in Europe, resulting in more than 5 billion euros per year in order to treat hearing-related issues. This problem is even more relevant when discussing for the Belgian defense personnel, where between 2013 and 2017, almost 200 were treated medically for problems related with hearing losses. In the United States, this problem is even more relevant, where the cost in order to treat veterans affected of hearing-related disabilities has increased drastically over the last 20 years. This, however, is a problem that is also relevant for the civilian. In fact, the civilian living near air bases here in Belgium, on top of experiencing annoyance given the noise emitted by the F-16 and currently F-35 during trainings, can also experience sleep pattern disruption, generalized anxiety, psychological symptoms, and in the worst cases, hypertension. But what is noise? At the core of it, noise is simply a form of energy that travels through the air as a series of compression and rarefaction waves. If the distance between the peaks or the compression is small, we have a high-frequency noise. Instead, if the distance between the peaks is more wide, we have low-frequency noise. If a signal contains only one frequency or the energy is concentrated around a single frequency, we call it narrowband, as you can see in this graph, where on the x-axis we have the frequency content and on the y-axis we have the amplitude of the signal. If instead the signal contains a wider range of frequency, it's instead called broadband or wideband. Additionally, the signal can be impulsive, like for example in firearms, or continuous, for example in jets, where in the second case the amplitude level is more constant within time, and in the first case instead we have a clear peak of amplitude. However, even though as said previously, noise is a variation of pressure, Pascal is not often used when discussing noise level. The reasoning behind this is that the human ear responds logarithmically to noise. For this reason, we developed a specifically matrix called decibel, where the zero, or the threshold of hearing, corresponds to a pressure variation of 20 micropascal, and a limit can be set at 140 dB, which is the threshold of pain, above which potential hearing damages can become permanent. Additionally, also, the human ear does not have a linear response when it comes to the frequency content of the signal. For this reason, also frequency weighting matrix is also used in order to mimic the human ear frequency response. A really common one is A weighting, where the low frequency content of the signal is reduced in order, then again, to mimic the human ear response. Other metrics, of course, exist in order to describe the sound, and a really nice way to visualize them is in relation of a sound event, in this case a flyover of a jet. First of all, we define this sound event as the portion of signal which is above a certain threshold, which is usually set as the background noise level. The total energy contained in the signal is called equivalent continuous sound level, which can also be seen as the average decibel level within the sound event. The peak or maximum level are also the maximum decibel reached within the signal. And finally, another important and relevant metric is the sound exposure level, or SEL, which is as if the entire energy of the signal was contained in 1 second instead of the event duration, which is in this case 90 seconds. Additionally, also psychoacoustic metrics are used. The reasoning behind the addition of these metrics is that two noises can have complete different annoyance to a subject even though they showcase similar decibel level. Therefore, these metrics can help us determine how annoying a particular noise is through the use of loudness, sharpness, and roughness. For example, let's consider a trumpet and a military jet flyover. Although they showcase similar decibel level, even higher in the case of the trumpet, when we look at the loudness, that gives us information on also the frequency content of the signal. Additionally, on top of the amplitude, we see that the military jet flyover scored much higher values. Instead, if we take a look at sharpness, which tells us the high frequency content of the signal, we see that trumpet scores much higher value compared to military jet flyover, telling us that in fact a trumpet noise is actually sharper.
To understand how noise affects us, we need a very quick overview of the auditory system. Sound enters the outer ear, which acts like an acoustic antenna. It collects sound from the environment and guides it through the ear canal to the tympanic membrane. Here, the vibration is transmitted to the middle ear, where three tiny ossicles amplify the motion. This mechanical amplification is essential to efficiently transfer sound energy from air to the fluid-filled inner ear. In fact, the inner ear, we have the cochlear. This is our biological frequency analyzer. As sound travels along the basilar membrane, high frequency peak near the base, while low frequency propagate farther toward the apex. At this location, mechanical vibrations are converted into electrical signals by specialized sensory cells and transmitted to the brain via the auditory nerve. Hearing loss mainly arises from two mechanisms, aging and noise exposure. Even in the absence of an excessive noise, hearing sensitivity gradually declines with age. This loss primarily affects high frequencies. As we move from 20 to 70 years old, we see a steep drop in sensitivity above about 4 kHz. And if we compare a 20 and a 70 years old guy, you will see 60 decibel of loss of sensitivity. The second mechanism is noise-induced hearing loss, shown in the bottom graph. The shape of the curve, in fact, is different. You can see a characteristic notch around 4 kHz. Why? This frequency region is very vulnerable because the human auditory system amplifies sounds between 3 and 6 kHz. Unfortunately, this is exactly the frequency range where many intense sound sources operate, including firearms, sirens, jet engines, and explosions. As a result, the noise-induced hearing loss not only reduces hearing sensitivity, but actually damages the most sensitive region of the human ear. If we zoom a little bit inside the cochlear, actually there are two types of sensory cells, the outer and the inner hair cells that you can see. The outer hair cells, they are our amplifiers. They boost and fine-tune soft sound in around the 4 kHz region. They are crucial for sharp and clear hearing. The inner cells instead are our sensory receptor. They convert the vibration into the electrical signals that travel to the brain. You can see that these are pictures from real microscopic images of the cochlear. On the left, you see a normal healthy cochlear where all these cells are very well organized and intact. On the right, after exposure to loud noise, many hair cells are visible damage. And unlike many other cells in the body, hair cells do not regenerate. Once they are lost, hearing loss is permanent. So that's why in this type of noise exposure accumulates over a person's career. So be very careful, otherwise this is what could happen to your ear. Now let's talk about an important question. Which is more dangerous, an impulsive or continuous noise? Let's first hear an impulsive noise. This type of noise is characterized by an extremely fast rise time, often an order of microsecond, and this is far too fast for the middle ear acoustic reflex, which is a muscle in our ear, to provide any protection. As a result, impulsive noise can cause direct damage to the cochlear, particularly to the hair cells. In fact, a single impulse usually is sufficient to produce permanent hearing loss. And because of the short duration and extremely peak levels, you cannot actually predict very well with standard metrics. Let's now hear a continuous noise. As you hear it, it was quite long. In fact, the damage mainly occurs from energy accumulation. As well, the risk increases with exposure time, and usually is very well described by LEQ and LAQ models that my colleague talked before. So to answer to your question, both are dangerous, but in very different ways. Before talking about wave propagation, it is important to understand what we mean by linear versus non-linear system. A linear system is very predictable. The relationship between input and output is proportional, and the system does not change the shape of the signal. That's why linear systems are simple and easy to model, and most classical acoustics belongs here. An example is a speaker. If you increase the volume, it will increase mostly linearly. A nonlinear system instead behaves very differently. The output is not proportional to the input. A small change can produce a large effect. You get distortion, saturation, steepening. The system becomes much harder to predict. The cartoon illustrates this perfectly. In a linear world, the ground is flat. Each step is the same. In a non-linear world, one small step can send you off a cliff. And this is exactly what happens physically in high-intensity noise. Once the system passes a certain threshold, the behavior changes dramatically. And this is extremely important for our work. In fact, systems like F-35 or weapons like SCAR produce very large pressure changes, much larger than normal acoustic, which means the propagation is non-linear, and linear models cannot describe their behavior. At low amplitudes, sounds propagate linearly. Waveform is preserved. That's what you see with the blue curve. At high amplitudes, however, propagation became non-linear. In this case, the local wave speed depends on pressure. As a result, the waveform progressively steepens and may eventually form a shock-like front. I added two audio examples to make this difference audible. The linear wave sounds smooth like a pure tone. Let's hear it. The nonlinear wave sounds sharper and more aggressive. This is because the waveform steepens and generates high frequency harmonic. And you can see this in the frequency spectrum here. The linear wave contains all this energy at one frequency. Instead, the nonlinear wave exhibits strong peaks at integer multiple of the fundamental frequency. These are the harmonics, and these are created by the nonlinearity, and this the frequency component that the human ear perceives sharp, annoying, and potentially damaging. And now we reach a critical point. Most commercial acoustic software and many regulation models assume linear propagation. As a result, they cannot reproduce waveform steepening and fail to generate the high frequency energy observed in a real measurement. This is a classic example from actually a measurement in a military firing range. Linear model, like some planned, significantly underpredict the mid and high frequency content of the measured signal. Why our nonlinear solver in red reproduce the spectral shape much more accurately. And this is why nonlinear propagation modeling is essential for high-intensity sources, such firearms and jets and explosion. And it's not only for to be accurate, but it's only for risk assessment and the protection of the soldier as well as the civilian.
We can clearly see the importance of nonlinearity and the higher amount of high-frequency content in the propagation when looking at the noise prediction and propagation on different weapon systems. In these graphs, we can see the amplitude on the y-axis and the frequency content on the x-axis. And in the graph, we can see in red the nonlinear prediction, in blue the linear prediction, and in green the experimental results. We can see that if at 30 meters in all weapons, both in the SCAR-L and the howitzer, the levels at a high frequency are contained and more or less the linear prediction does a good job on predicting noise, the noise level, when we move farther away from the signal at 183 meters in the case of the howitzer and 250 meters almost in the case of the SCAR-L, the high frequency content is much higher than what expected. And in fact, the only propagation that matches the experimental result is the nonlinear one. Interestingly enough, this higher amount of high frequency is present also on smaller weapon systems like the 9mm pistol, where we can see that also in this case the linear prediction fails to correctly predict the high frequency content of the signal. This is also true when looking at the results from military jets. In fact, if considering microphone position at 305 meters from the source, so from the jets, in the case when the engine is in idle condition, so at the lowest power setting, more or less the prediction of the linear and nonlinear one are almost identical. But in afterburner conditions, so the highest power setting available on the jet, we have a clear difference where the linear prediction completely fails to capture the high frequency content of the signal, which instead is perfectly matched by the nonlinear prediction. Additionally, when looking at the results of the F-35, we can see that even at almost over 1 kilometer, the high frequency content of the signal is much higher compared to what we expected. And the fact that this higher frequency is due to nonlinearity can be also checked by the use of a particular metric called the derivative, the skewness of the pressure derivative. As we can see for multiple jet runs of the F-35 at above 1 kilometer, it scores really high value, even above 5, which is an underlying factor of the importance of and the presence of nonlinearity in such noise propagation. When it comes to the model that we developed and we currently use in order to have noise propagation, the first step is the experimental side, so the actual measurement in outdoor conditions of the noise emitted by firearms and military jets. The need for experimental result is double. On one hand, the way our propagation system, our propagation model function is that we need to feed the numerical solver a realistic recorded signal that then is propagated at the wanted distance. Additionally, the need for experimental result in order to perform validation process of the result of the numerical solver. When it comes to the actual solver, it is entirely based on this equation right here. I won't go into details of this equation, but the interesting fact is that as you can see, each terms within this equation serves a purpose of describing one of the way sound propagates through space. So taking into account geometrical spreading, atmospheric absorption, nonlinearity and refraction, as well as diffraction. Additionally, within the model are also included additional equations and conditions in order to treat both the boundaries and the ground reflection. The end product is the video showcased in repetition on the right side, where you can see the wave traveling through space captured by our microphone and the results of the NP simulation almost matching basically exactly the measured ones. Circling back to the actual way the solver works is work as a computational window, so basically a portion of the domain in which the initial wave is defined. This computational window is then propagated through space, and at the wanted distances we can take a snapshot of the pressure field. Once the pressure field is known, so we can know the position of the front of the wave and the amplitude, we can easily calculate all the relevant acoustic quantities. Finally, it's important to discuss uncertainty, which is a key factor when discussing outdoor noise measurement. Uncertainty itself can be either systematic, so it does not change when measurements are repeated, and it can be due to the shortcomings of the instrument, like for example the tolerances of the instrument itself, or it can be random, so it changes unpredictably from one measurement to another. One of the reasons by the random uncertainty is, for example, short-term changes in the environmental condition, like for example the change of wind speed or wind direction, which, as you can see in the graph, which is a real measurement of the wind condition, can change drastically even in the span of few minutes. Before concluding this webinar, I would like to share with you two phrases. The first one is, to win a battle, you must first know your enemy, which is the motto of both me and my colleagues when it comes to our project. In fact, even though the final goal is to defeat the enemy, so defeat the noise and the hearing losses, we must first know it, so having a complete understanding of how noise behaves and propagates. The second phrase is hearing protection, a sound investment. Picking up a good pair of protective headphones and using them at the right time, it doesn't cost anything, but not using it could cost your hearing for the rest of your life. Thank you very much for your attention.